Geology, geology, geology. Welcome everybody to the Mini Geology Show. This is Daniel Minisini, your inquisitive geologist. And today we'll talk about questions. Asking questions is a part of the joy of science. One good question can give rise to several layers of answers. It can inspire research. It can generate a whole new fields of inquiry. And as you know, we like to inquire in here, and questions can prompt changes in entrenched thinking. So we have with us Kim Kastens from the Lamont-Doherty Earth Observatory in Columbia University, New York, for helping us with this very important task. Hello, Kim.
Hi, Daniel. How are you? It's great to be here.
We are very good in here, and we are so glad to have you to talk about an overarching topic that stays above science and so for sure above the beloved geology. And so very, very welcome. Asking questions is a necessary step towards many activities like formulating hypotheses, making decisions, solving problems. And I'm above all wondering, how did you come up with this, studying the way in which questions arise?
A fascinating question in and of itself. Well, I did not used to be a good question asker. When I was an undergraduate and even a graduate student, I did not ask very many questions. I did not really think very much in terms of questions. But then I gradually began to ask more and more questions. But truthfully, it wasn't out of science that I developed this interest. It was from teaching journalism students. So for a while, I ran a program, a master's degree program for people who wanted to be earth and environmental science journalists. And I found that some of the students who came to the program were excellent question askers. They had a real gift for asking questions that would bring forth important and interesting answers from their interviewees. Whereas other students who also had very good science backgrounds, very good writing backgrounds, looked like really strong students on the face of it, they found it very hard to ask questions. They found it very hard to lay their ignorance out on the table in front of the interviewer and say, you know, I don't understand this, explain this to me. And so it was through watching journalists and journalism students and trying to figure out how to teach journalism students that I became aware that asking questions was a skill, an important skill, a skill that some people were better at than others, and a skill that could be practiced and learned. One other thing happened. I made a mid-career change in my direction. As you know, I originally worked in marine geology, working in the Mediterranean, and then in mid-career, I switched into instructional technology and geoscience education research. And in my old career, I was not a good question asker, but in my new career, I became a very good question asker because I didn't know anything. In my old career, I felt like I should know stuff. I shouldn't, be asking these stupid sounding questions because I should know those things. But in my new career, I had no inhibitions about asking questions. So I observed this change in myself. I observed the difference in my students, and I thought, this is really important. And then along came the next generation science standards and the framework for K-12 science education, which place asking questions as scientific practice number one. So that sort of confirmed in my mind that this was really important and needed more attention.
Can you describe that milestone in which you turn around and you move from being a marine geologist, very well recognized, into a completely new professional?
Yes. Several things fed into that. One was personal and the other was the time. I had my first daughter, Holly, was born, and I had been in a style of life where I spent several months a year at sea, and my husband, who's an oceanographic engineer, spent many months a year at sea, and I couldn't see how to keep doing that. So there was that. but also I felt the field was becoming less interesting. So when I first started doing marine geology, it was soon after the plate tectonics revolution, and there was lots of low-hanging fruit. You could hardly take a ship to sea without discovering something important. And I felt that the effort to insight ratio in my field was becoming less favorable. It was becoming harder and harder to discover something interesting and important. So I felt the field was not at an optimum stage, and the lifestyle required for the field was not going to be a good match for me going forward. And so I looked all around the periphery of geology, looking for a field that was in a state of great discovery, the way marine geology and plate tectonics had been when I first got to graduate school. And I discovered learning technology, instructional technology, and I began to work with the Teachers College Institute for Learning Technologies. And I found sort of a second field that was in this state of great discovery and invention. And
when did it happen? Which year?
1992. So my last seagoing trip was 1993, the Vima fracture zone.
And so now, after those many years, now is more mature, the field that you're studying.
Yes, my new field is now mature as well.
And how have you evolved yourself in this path of maturation in your studies around questions or many other things?
I have been very fortunate in having fabulous collaborators. So I've been able to collaborate with many excellent cognitive scientists and learning scientists. So beginning with Robbie McClintock at the Teachers College and Lynn Libben at Penn State, a psychologist. My current collaborator is Tim Shipley at Temple University, another psychologist. So I have been able to find great people to work with. Toru Ishikawa, who's now in Japan, was another cognitive scientist that I worked closely with for a number of years. And the way to work with a collaborator outside of your field necessitates asking questions. So the way to learn in a field where you want to make progress, but you don't have the formal training, one way to do that is to find a curious collaborator and ask lots of questions and be willing for them to ask you questions in return. So the questions come from both directions when you're trying to build an interdisciplinary collaboration.
What is the key question that you are trying to solve nowadays, since you have now a career that stretches from 1992, 93 to 2020?
Yes, the question that I am trying to understand right now is how do humans, experts and novices and everybody in between, reason with feedback loops, positive and negative feedback loops, reinforcing and balancing feedback loops.
Can you give us an example?
Yes, so a feedback loop is can be defined as a situation where some event or phenomenon, let's call it A, influences some other phenomenon, let's call it B, and then B in turn influences A. So there might be some other steps in between. It might go A to B to C and then back to A. But the key thing is that it goes, the chain of influence goes around in a circle and comes back to A. An example from geosciences would be the atmosphere gets warmer and that causes ice in the Arctic to melt, which causes the albedo to change because there's less shiny white ice in the high latitudes, and therefore less is reflected back to space and more is absorbed into the ocean, and therefore the ocean and the atmosphere then become warmer. So
how would you pose this technical question about the feedback loop? What is exactly the question that you're trying to solve?
We have noticed that this seems to be a very difficult topic to teach. So we have some methodologies for testing students' ability to generate feedback loops, to recognize feedback loops. And we're now trying to understand how to improve students' ability to generate feedback loops. We have a hypothesis about that, and we're trying to understand why it is that this is a difficult line of reasoning for humans to
Okay,
figure out.
so the point is that is a difficult line of reasoning. The feedback is not
It's
easily
difficult.
understood.
It doesn't come, so
It's not
like
intuitive.
like everything else, there are big individual differences. Some people get it right away and some people really struggle with it. But in general, many instructors report that it's a hard topic to teach, or that students understand it only at a pretty superficial level. So we're trying to figure out what teaching strategy can help get past those difficulties, and that at a more fundamental level, what is the source of those difficulties?
Kim, we almost reached the metaphysics. So do you have any specific thinkers, philosophers, or scientists that they influenced you to make that big change in '92, but also that inspires you during these last 3 decades?
Well, that's interesting. All of the collaborators that I mentioned earlier have all been very influential to me. But also, I have been surrounded by career changers and boundary crossers for my whole life. So boundary crossers are people who have an expertise in one field and step into another field to do, sort of their next phase of their work. So my father was a boundary crosser. My undergraduate thesis advisor at Yale, I was a geology major, and I worked on sand waves in Long Island Sound, and my advisor there, Dr. Robert Gordon, had changed from rock physics, squeezing rocks, to working in coastal geology in Long Island Sound, and that was where he was at in the phase that I worked with him. And then after that, he changed into archaeology, sort of at the intersection between geology and archaeology. So he was a boundary crosser. My PhD advisor was a boundary crosser, Fred Spies. He went from sort of classic physics into ocean engineering, and he mentored a huge number of graduate students across all the disciplines of oceanography. So he had students in biological oceanography, chemical oceanography, marine geology like me, ocean engineering closest to his own expertise. So he was a very interdisciplinary sort of a. And then my postdoctoral advisor, Bill Ryan, you may know him from the Mediterranean as well. He worked on a huge range of topics. So he worked on, the drying up of the Mediterranean. He worked on Noah's flood. He worked on passive margin geology. So my whole career has been surrounded by people who made their contributions by making a leap from one field in which they had an established body of knowledge and expertise into another field where the contributions that they could bring were unique to that field,
That's
were
fantastic.
special.
So I hope you also know very common people. I mean, let me hope that you know also common people that they
Sure.
stay on their discipline, so that you can compare and contrast to let us know what is special about this boundary crossers, that you have this luxury of having them surrounding you for so much time.
I don't really know. I didn't seek them out, but it is true that I have had this lifetime of exposure to boundary crossers, and I think that helped me become a boundary crosser. It is very tightly coupled to the question asking issue, though, because when you come into a new field, you don't come with assumptions, and you do come with it kind of gives your curiosity a jolt to be surrounded by all sorts of new stuff, and makes it possible for some people to be more creative than they were able to be in their old field. I think, you know, science absolutely needs people who stay very focused on, you know, one important question from their PhD thesis, you know, on into the date of retirement. There's certain kinds of progress that can only be made by that long, persistent attention to one line of research. But there's also definitely a place in this world for people who change careers.
But nobody teaches this. Nobody at the university, there are no teachers that are telling the students, look, at some point in your career, be prepared that you could all of a sudden change topic. And you have to have not only the courage and the spirit, but you need also the responsibility to take that role.
So I think that every new field begins by being populated by boundary crossers. So I was in the first generation of scientists who could get trained at the PhD level in marine geology. The generation before me, which included Bill Ryan, for example, he came out of physics, and all of his contemporaries came out of some other field. There was no specialized training in marine geology. So everyone in his generation came out of either terrestrial geology or physics or biology or chemistry or engineering, some other place. So every new field, the only way a new field can get created is by boundary crossers. And so, you know, for science to expand into whole new domains, there has to be a mechanism for boundary crossing to be possible. As the field becomes more and more established, boundary crossing becomes more and more difficult. So I was not a boundary crosser in marine geology. I went to a degree program that was labeled as you know, marine geology. But when I changed into instructional technology and then into geoscience education research, those were both brand new fields. They didn't have an established set of, you know, wise elders who had populated the field already. Everybody was coming into those fields from someplace else. But once the field gets very well established and there's a big literature and there's, you know, well-established senior scientists in the field, it gets harder and harder to boundary cross into such an established field. You can't just, it's just not as welcoming when it's a very well-established field.
Yeah, then you grow up inside that discipline.
You grow up inside the field, that's right.
Yeah, yeah. And moving into this question asking topic that you develop and that you have been publishing about, what is the question asking behavior of learners with respect to teachers? What is the difference? What are the basics?
Well, let's see. Before I go any further down the question asking route, I want to credit my co-authors. So I did this question asking work with Margie Turrin from Lamont-Doherty Earth Observatory and Melissa Zrada, who is now at the College of New Jersey. She was at Teachers College when we did this work together. So I just wanted to make sure I didn't forget to say that. So the difference is that in most classrooms, teachers ask many questions and students ask few questions. Lots of students never ask questions in their science class. The teacher may say, you know, may finish explaining something and then say, are there any questions? And that could be either a high school or middle school teacher, or it could be a university professor. And then one or two people raise their hands and then they have a question, and you know, the teacher answers the question and then the topic goes on. But most students ask no questions at all. And teachers ask the questions, students provide answers, and that's the normal pattern in most classrooms. So this is really, if we accept what the K-12, the framework for K-12 science education tells us, and our own experience as scientists tells us, which is that asking questions is a central practice of science, it's a real mistake to have a classroom norm where students are not asking questions in science class. that has to change. There has to be a mechanism for asking questions to be an expected part of the cultural norm of science classes for every student.
Kim, can you apply this also for seminars or talks? You know that they're like 1 hour long, and they occur not only in the universities with professors and students, but in academia between professors and in industry between professionals. Is that something wrong in the typical PowerPoint presentation of 40 minutes and then 10 minutes Q&A?
I have a few suggestions. This is not something we researched, so this set of suggestions comes strictly from my informal observation and not from a research project. But there's a couple ideas. One is, instead of saying, are there any questions? You say, what are your questions? So the first implies that, did I explain something badly, or are you stupid? Just basically, are there any questions? Whereas if you say, what are your questions? That implies that, of course, you have questions, and I'm eager to hear them. So that's one thing you can do. Another thing you can do is have question opportunities several times during the seminar. So in other words, when you come to, you finish part 1, then you pause and ask for questions on part 1, and then you pause again and ask for questions on part 2. So it's easier for people to remember their questions and still care about the questions if you stop a few times during the seminar. And then finally, especially for a seminar that's attended by students, you can ask for questions in advance to be sent to the speaker in advance. And you could even require questions to be sent to the speaker in advance. So you could, for example, have the students in the seminar read a paper or look at a data set that's produced by or relevant to what the seminar speaker is going to speak about, and then give them either the opportunity or the requirement to formulate a question in advance. So that helps the speaker know what the audience is interested in, and it gives the speaker a better calibration of the audience's level of knowledge or ignorance.
And based on your studies, what is the conclusion on how the questions come to life?
How the questions come to life? Well, one thing that we definitely concluded from our study is that you can elicit good questions by just asking for questions. So in our study, we were working with undergraduates, and we had a diverse population from many different colleges, many different majors, all in the sort of Boston, Cambridge area. But there was a lot of variation in the students' knowledge of the kind of, we had them look at data and ask questions about the data. The data all had something to do with climate change or sea level change. And we used 2 different prompts. One was write down as many questions as you can about what you're looking at. And the other was, imagine you're going to have a chance to talk to the scientists who collected this data. What questions would you like to ask those scientists? And in both cases, we got lots of questions, and we got good questions. We got good questions from people who knew nothing about the topic. So we got good questions from science majors, good questions from non-science majors. And so just giving students a prompt, giving them materials. In our cases, they were maps of things like sea surface temperature and air temperature and location of tsunamis and hurricanes and other kinds of all earth science and social science topics related to climate change and sea level rise. Just, asking for questions gets you questions, but we hardly ever do that. We hardly ever, and they wrote down their questions on a form on a piece of paper. So they didn't have to speak aloud their questions. They didn't have to, sort of confront the interpersonal dynamic of asking questions. They wrote down their questions. And we got lots of good questions. We got lots and lots of questions of all sorts, and we got good questions. So the first thing is that you can get questions if you just ask for them. So this can be an assignment. This can be an assignment required of every student. It doesn't have to be merely a kind of informal seeming opportunity for the handful of people who raise their hands in class. So that's one thing. The other is that earth science data sets are great for generating questions. So in particular, we had data sets that were more oriented towards the consequences of climate change and sea level rise. Earth science data is a good stimulus for
is this
generating questions.
the reason why geoscience or geology in sensu stricto is different than investigating questions in other sciences or other disciplines?
Well, I have a couple thoughts about that. One is I really hope that somebody will replicate our study in other fields. So in geoscience, in our study, we use maps as the stimuli. In biology or physics, you might want to use graphs or some other kinds of data displays. You might use, neural images or some other kinds of data. So I think that it would be fascinating to replicate our study with other data types. However, I do feel, and this actually goes back to the very first paper I ever wrote when I was making this, this career change. I do feel that in earth science, the boundary between the known and the unknown is closer to lived experience. The kinds of questions that we ask at the frontiers of earth science are comprehensible to the lay audience in a way that the questions at the frontiers of, another field, perhaps biochemistry or particle physics, would not be so accessible to the lay audience. So, why did dinosaurs go extinct? Or, how hot is the Earth going to get by 2050? These are questions that are quite accessible to middle school kids or your basic lay audience. So the boundary between, so science advances on this thin frontier. You can sort of imagine this amoeboid shape, and inside is what's known, which is finite, and outside is what's not known, which is infinite. And the place where you can actually do science is like right on that thin little membrane between the known on the inside and the unknown on the outside. And I envision this membrane as having sort of, protrusions and embayments. And, I think that in earth science happens to sit at a place right now where the boundary is relatively close to the lived experience of the lay audience. So I do feel as though it may be more possible to generate lots of good student questions in earth sciences than it is in other fields, but that's purely speculative. The study should be replicated in other fields to see how true that really is. But it definitely works in earth science. So definitely something that, that every earth science teacher could be using.
And so what are the factors that they influence the kind of questions that the students pose?
Well, the first thing that we had to do was figure out how to categorize questions. And so a lot of our effort went into actually categorizing questions and then trying to understand what constituted a better question and a not so good, not a more scientifically generative question and a not so scientifically generative question. So we collected hundreds and hundreds of student questions, and then we tried to sort them all out into categories. And so we ended up making this taxonomy of types of questions. And then we ranked the different kinds of questions according to how cognitively challenging they were. So at the least cognitively challenging end of the scale would be what we categorized as please explain questions. So that's where they're saying, what does red mean on this map? What do dashed lines mean on this map? Or alternatively, you've told me that this is a map of sea surface temperature, what does that mean? What does the entire category mean? So those would be the kinds of questions that must be answered before the student can make any progress at all in making any sense out of the data. And the thing is that those questions are necessary. When I look at a kind of data that I've never looked at before, I have to start with those please explain questions. I'm looking at some data set that comes out of some cognitive science lab, and it's a kind of data I've never looked at before. And so I'm asking these same questions. Well, what does blue mean? You know, what do these squiggles over here mean? And so that would be the lowest cognitive level question. The highest cognitive level question in our ranking scheme would be questions that are where the questioner has observed something in the data that doesn't match what they expected to see. So we call that departure from model. So for example, a student might be looking at a map of water temperature data in the oceans. And there's, their model was that, well, it would be hottest at the equator, and then it would get gradually cooler and cooler as you went north and south from the equator, kind of uniformly. And they'll say, hey, it's really not like that. It's much, it's asymmetrical. There's, one ocean is warmer than the other at the same latitude. Why is that? In other words, they had this model and they're seeing something in the data that disagrees with what their mental model was. And so that would be departure from model. And then another high cognitive level question would be a question where they're offering some kind of a process or mechanism or a hypothesis that has to do with where they have an idea about what might be explaining something that they're seeing in the data. So anyway, so that would be the two extremes of our continuum. So we're just barely beginning to get a handle on what causes, what brings forth good questions, what brings forth not so good questions. The two prompts we use bring forth different kinds of questions. So there's an important kind of question, which is a question about how the data was collected or analyzed. And that kind of question is preferentially elicited by our prompt to imagine that you're going to have a chance to talk to the scientists who collected the data. What would you ask them? So different kinds of prompts can bring forth different kinds of questions. And we actually think that, a very wide range of kinds of questions is good. And so we would encourage using different prompts. The people who have stronger science backgrounds tend to ask questions that are the process mechanism kinds of questions. We didn't look very carefully at that, but that seems to be the case. Let's see. A few things that we thought might make a difference but did not. We gave half of the students the data to look at on an iPad, where it was interactive. They could zoom in, they could pan around the world. They could, for example, step down to different levels in the ocean. And we gave the other half of the students the same maps, but in paper atlases. We made up paper atlases out of the same maps that were in the iPad. And it didn't make a bit of difference. There was virtually almost no difference in the types of questions that emerged in those two conditions, the paper map condition and the interactive
So
condition.
I understand that you, as a teacher, you have the reins to decide where to bring your students accordingly to what you present them. Is that correct?
That's right, yep.
Almost more importantly than the background of the students.
The background of the students is certainly important. You have to build on what they have already. But you have, particularly with respect to these things that the framework for K-12 science education calls science practices, as a teacher, you have a great deal of opportunity to foster different science practices. And the thing about question asking, the thing about developing the habit of mind and the skill of question asking is that it lets you keep on learning after you leave school. So our most, brilliant teaching modules can help a student learn something important and insightful while they're in our classroom. But eventually they're going to go out in the world and we won't be there for them anymore. And so how are they going to keep going with their learning? And so we can help them by helping them develop a toolkit that will enable them to be self-directed learners for the rest of their lives. And asking questions is right at the heart of that.
And in your experience, do you see differences in posing questions by gender?
We did not look at that. And let me think about this. There is some other literature of people who have looked at that. There are some papers written about the kinds of questions that get sent into websites that are called Ask a Scientist website. So you can type in your question into your web browser and it'll get sent out and answered by some scientist. And those questions have been studied with that question in mind. And one finding that I remember is that females asked more biology questions and males asked more physical sciences questions. So
what about by race?
We didn't study that, and I don't know of anybody who studied it in a study similar to ours. But what I can tell you is there is literature on sort of cross-cultural comparisons of question asking. And there are cultures where question asking by young people, especially question asking of authority figures, is discouraged, is considered inappropriate behavior for a child or a young adult. And as instructors in colleges that have diverse populations, we need to be sensitive to that. We have to, basically, if we're going to make the case that, okay, this is a science class and asking questions is a norm of science, and therefore asking questions is going to be something that's expected of every student in the science class, we have to anticipate the possibility that both some individuals will find it harder than others, just like my journalism students, but also that students from some cultural backgrounds will find it harder than students from other cultural backgrounds.
So I understand that educators in general, they agree that teaching science should involve more inquiry-based learning rather than learning facts and memorization. So we arrived to that moment when I asked you, how can you teach the art of asking good questions? Because you said there are different levels and you want to bring your students to ask the best questions, which, as you explain us, are the ones with the more cognitive content. How do you teach them?
So again, our study didn't go there. We studied existing questions of students who had not been instructed in the art of asking questions. So I can't give an evidence-based answer to this, but I have some ideas that are definitely worth trying. And the first is to just require question asking, just assign question asking as something that you do when you encounter a new topic. I would recommend having the students ask questions before you tell them the answer. So in other words, have them ask questions about a new topic when you've just introduced a new data set or a new paper, rather than afterwards. And the reason for that is that they're then invested in the answer. So you are going to start talking about a new topic. If you invite them to ask questions at the beginning of the topic, then they're waiting to hear the answer. They have some investment in having the answers come forth to the questions that they've asked. That would be one idea. Another idea is to share our taxonomy of questions with the students. So There's an elaborate version of the taxonomy of questions in our JDE paper, and there's a simpler version of the taxonomy of questions in
Why
our...
would it be important?
Pardon?
Why would it be important to show the taxonomy of questions?
Because otherwise, what you want to avoid is inquiries where students are inquiring about questions that are not scientifically meaningful. So one of the papers that we cited, I can't recall the author right offhand, but he basically is writing about middle school students who are doing a science fair experiment to see whether or not plants grew better with Coke or 7-Up. So, you know, whether it is an inquiry, it is an actual question that is answerable with the scientific method, but it is not a question, as far as I know, that attaches to, you know, the border between the known and the unknown in life sciences. And so basically students need to understand that in order to find a question that's worth researching, it's hard to find a question that's worth researching. You have to ask question after question after question after question. And most questions, when you're trying to start an inquiry, it turns out most questions that occur to you, they're either questions that have already been answered, or they're questions that cannot yet be answered. So this boundary between the known and the unknown is a very thin membrane, and it's only in that very narrow zone where questions can actually be answered through the methods of science at this moment in time. You need a question that has not yet already been answered, and you need a question that is answerable given humanity's current knowledge and suite of tools. And so you need to just ask lots and lots of questions, and you need to expect that you're going to have to throw out most of the questions that you ask when you're looking for an inquiry. And I did not used to understand that, actually. I used to think that basically any question that I could find that had not been answered and that was answerable was worth my while. And I spent a bunch of time early in my career answering questions that I now think were not a good use of my time. They were not interesting or important questions. I truly didn't know that some questions were more interesting and important than other questions. I had no
Who decides that? Who gives the moral touch to those questions, saying this is more important than this other question?
That is a really good question. Different people do, you know, journal reviewers do, proposal reviewers at funding agencies do.
But they are part, this couple of that you mentioned, they are part of a system.
They are part of the system.
They don't have a genuine not interest approach to your question. They're gonna think if this is useful for them or if there is useful for society because somebody tell them that it has to be useful for society.
Well, that is true. So questions can be worth answering for multiple different reasons. One reason can be because society needs, you know, that they bear on solving a problem that society needs to be solved. Then there's another set of questions that are worth asking that are valuable because they illuminate a whole new piece of human knowledge that we haven't been paying attention to previously. So when plate tectonics came along at the very, very beginning of my education, all of a sudden, lots of new questions were possible. Lots of new questions that couldn't have even been framed previously. So that set of questions filled in a big gap in human knowledge that hadn't previously been accessible. So a door opened to a whole bunch of new questions when plate tectonics framework came along with which to think about the Earth. But as far as helping students recognize what constitutes a good question or not a good question, I think they should realize that these please explain questions, they have to be asked. They shouldn't be something you should be ashamed of. You have to ask these please explain questions if you're going to engage in a substantial way with the data. So, but after that, then you want to work up to the next kinds of data. So the next kinds of questions are questions where you're seeing patterns or trends in the data and wondering what is the cause or what is the consequence of this pattern or trend. And then after that, you want to begin generating hypotheses about why is the Earth behaving with the attributes that I'm seeing in the data. And then after that, perhaps noticing or wondering why it is that the data does not appear to be matching the models that you've been taught of how the world is supposed to work. So students can learn that, they can learn that question asking is important. Question asking is a skill that can be improved through practice, and that there are different kinds of questions, and that as they begin to work their way into a new topic, they can ask more and more generative questions until finally they've got a question that sits on the boundary between the known and the unknown, and that is worthy of their attention as a young scientist.
Well, let's talk about that question. Can I call it a key question?
Sure. Yep.
Okay. So so you explain to the students how they have to narrow this plethora of questions. First, vertically, so getting rid of the simple questions and going to the more difficult, and then drying out to find that key question. And I ask you, what are these processes that happen in our mind, the cognitive processes that they come into play during the generation of these key questions? This is the most important question to me.
Yes, and I believe that is almost non-researched. So we looked for literature on this topic while we were doing the background for our paper, and we could not find much written at all on where do scientists get their questions from, approached from a sociological perspective or sort of a social science research perspective. There may be literature on that out there, but it's not particularly well known, at least to me. So what I had to go by in thinking about that is my own observation of excellent scientists around me. Lamont-Doherty is full of excellent scientists, so I got to watch lots of people do good science, as well as I like to read biographies of scientists. So I have sort of thought about where those questions have come from that they decide to work on. And I think one thing that's important is it has to be a question that you yourself find fascinating. So in other words, this isn't a one-size-fits-all business. A question that would be a great line of research for me would not be interesting to the person down the hall. So it has to be a question that's fascinating to you personally. I think that for many people, it's very helpful if it is a question that has the potential to do something good for humanity or society. Not everybody is motivated by that way, but there is a whole category of use-inspired research where the question has the potential to make the world a better place for human beings in one way or another. And many people gravitate towards that category of questions. And you might argue that for two questions that are otherwise unanswered and of otherwise equal caliber, you might sort of give the tip to the one that has a connection to societal issues of one sort or another. And we're very lucky in our science because there's a huge number of questions that have some connection to something having to do with societal needs. So, you might argue that most questions in our science have something to do with societal needs. So that's good. And then after that, I would say a question that has the potential to to open the door to a whole new category of inquiry. The trouble is, I don't know how you know that in advance. So if we go back to the example of plate tectonics, who would have thought that looking at, magnetic wiggles of seafloor magnetic anomalies would have turned out to be a set of questions that would open the door to a huge and fertile domain of knowledge. I don't think that was at all obvious in advance. And I don't know whether Walter Pittman thought it was obvious in advance, but probably not. It's not always obvious which question is going to open the door to an important new line of work.
I'm surprised that there are no proper studies on such an important topic, especially during this last couple of years, 3 years, when we have the artificial intelligence and big data that is impregnating universities, industry, governments, defense departments, because if you could train a machine to find the key question through the protocols that you would provide,
Mm-hmm.
you could advance very fast in specific disciplines.
That is really an interesting possibility. I would not know how to instruct the machine. I would not know how to set it loose on the body of material that it would need to digest.
Well, one of the three elements that you propose, it could be trained. You said one is the fascination. So machines, I don't think they're fascinated. But the second one, that is good for society, the machine can be trained for that.
Yeah.
The third, maybe with some algorithms, since machines, they always win at chess, they can probably know if there are going to be other doors that can be opened to other disciplines. So 1.5, maybe.
Maybe. I'd love to talk to somebody who would like to try doing that. I think it would be a fascinating thing to try.
Yes, that would be probably. Now you should be again another border crosser.
Boundary crosser. Yeah.
Going to artificial intelligence to teach machines after students.
I think I'm in my final career. I think geoscience education research and is going to be my last career. But I probably thought that in marine geology too at one time. So.
Yes. Kim, thank you very much for all of these insights and for sharing your experience, your past, and this exciting moment in your life when you decide to turn around and have that milestone in 92, 93 to change your career, and now explaining us many other things. I remember I read a paper of yours in EOS, the magazine. You were writing, I think, multiple authors, probably also with Manduka, about the mindset of the geologist. That was completely new to me. And I remember reading that, how important I felt. I think, I thought, oh, I'm special. Look at that. I never thought that. I have this mindset that the others, they cannot never have.
That's right. Yeah. So that was a fascinating project. That was the synthesis of research on thinking and learning in the geosciences. And we had a collaborative team of cognitive scientists and geoscientists. And we matched them up in pairs, one cognitive scientist and one geoscientist, working together on spatial thinking, and one pair working on temporal thinking, and one pair working on systems thinking, one pair working on learning in the field. And we took everybody to a forest, actually, to a research and education forest up north of Lamont, and put everybody in a little remote locality for a week to talk to each other and try and understand each other's perspective. And out of that came several interesting things, but I think the most broad-reaching has been that thing about geoscientific habits of mind and how geoscientists think.
Very, very useful. I think that for me, that little short article and the mindset of my advisors, they were the key elements to allow me investigate geology through a different lens. So
it's great that you're doing all these interviews, though,
yeah.
because you are pulling forth insights about how geoscientists think and learn that otherwise are not being captured and recorded.
Yes, yes, and then I'm so lucky that I'm absorbing knowledge from all the people that I encounter. And keep in mind that generally I used to do it face to face, and now because of the virus we cannot do it. But on the other side, because I can go way beyond the city where I live, I can
That's
talk
right.
with you,
Yes,
and I can talk
exactly.
with people
So,
elsewhere. So Kim, we have still 1 or 2 minutes. If you want to say something more, the mic is open so that you can express all those things that you couldn't, because I derail and drift away from the main topic.
I just wanted to say that I think that how geoscientists think is really, really interesting. And it does come forth because of the nature of what we study. So we do study a complicated and complex and heterogeneous object, which is the Earth, and it's hard to understand. And so the strategies that we as a profession have developed to study the Earth are really interesting to think about. And just as in that paper that you found in EOS, I think geoscientists should be proud of and appreciative of the methodologies that they use, the habits of mind that they use for thinking about the Earth.
Well, thank you again, Kim Kastens from the Lamont-Doherty Earth Observatory in Columbia University, New York. This is Daniel Minizini, your inquisitive geologist, with another show of mini geology that you can find in minigeology.com. And you can write me at minigeology@gmail.com to ask more questions. Talking about questions, you can propose a person to having here. You can propose yourself to be interviewed. And thank you again. Hope that this is useful for you geoscientists and for society at large. And thank you again so much, Kim.
It was great. Thank you, Daniel. Bye-bye.